I want to tell you what to do when the shape is not a cylinder, it's not a plain wall, and you still need to give your boss an answer. So 4.3 in the book is arbitrary shapes. Look at this. This is when conduction is steady state, but not 1D. So all these things we've been discussing about isotherms and adiabats, here they come into play. There is a way even of doing these graphs intuitively, and you can still calculate important values. I'm skipping that. But this is a cool thing. Look at this. The concept of thermal resistance says Q equals delta T over R. That's the way we have defined thermal resistance, right? For the case of a wall, for a plain wall, we have done that. For a wall, we have R was for the case of a cylinder is for a case of a sphere. Look at this. Do you see some sort of a trend going in the way I wrote these equations here? Look, we're saying resistance of a wall is something that relates to the material and some sort of geometry parameter. Cylinder, same story. Right? This has nothing about the material, but all about the geometry. Look at the sphere. Again, a geometry and something about the material. Right? Material, sorry, view here. About the material. So, if it works for a sphere, it works for a cylinder, it works for a plain wall, how about, and here's where this is engineering at its best. Stay with me, because this is just awesome. Okay, so they say, all right, what we're going to do is say that the resistance for whatever you ever like is going to be this 1 over K, as we always have, something about the material, and something about the geometry. This, that they write as 1 over S, this is the shape factor. This is quite awesome, because now, to some extent, I haven't told you anything yet. But if somebody tabulated this based just on the geometry, you can apply it to any material, from balsa wood to diamond to steel to oil, right? And sure enough, it is tabulated. So here you go. You see these shape factors? They are tabulated in the book. Somebody, and is somebody you're happy you're not that, was doing triple integrals of solve the heat diffusion equation for these different geometries. A sphere buried in a semi-infinite medium, horizontal cylinder, isothermal cylinder, right? All these cases. And they say, okay, For all these cases, there is a shape factor. You put it here, you got your resistance. And now rock and roll. You know everything. Now you know everything else, because you know how to deal with resistances. Now these shape factors, they can look somewhat theoretical to you, and if you were to read the thesis of these people, it's just formulas. But to give you an idea, so for example, one of the treatments for cancer is that they inject some pellets under your skin, and then if you have the right electromagnetic wavelength, those things can get locally hot, right? And if they get locally hot, you can kill the tumor locally, right? It's a lot better than just radiation that kills everything on its path. How do you calculate that? Where do you go? You have the pellet under the surface of the skin. So you see these formulas. Never be fooled just by the black ink and the pixels. There is so much here, so much effort somebody did to come to this thing, which in the exam you're going to do like just in 30 seconds, right? And so much you can do with this, right? You have a fighting chance at very complex problems. And this is amazing. If you study physics, they'll say solve the integrals. If you study mathematics, they'll say what is heat transfer, right? But if you want to cure cancer, the doctor alone can do only so much. The difference between the doctors today and doctors 100 years ago is us. Is the technology. So that's a pretty cool thing. And you have, like, look, all these things tabulated. Remember when we say, let's consider a wall that is infinitely long and infinitely tall? Right. But if you want to calculate a beer cooler, which is essential, right? That has edges, that has corners. And you know what? You can do it exactly. You can do it exactly. Here you have how to cut the shape factor for the edges. Here you have the shape factor for the corner. Let me tell you, it's going to make very little difference. But if you obsess so much about your beer, I know it doesn't apply to any of us, but if you do, you can calculate it exactly, right? That's a pretty amazing thing, very, very amazing thing. So you have all these other geometries. The book has an example about, I think it's freezing rain, in which you would have an electrical cable here, and you would have like the coat of ice that is not concentric. And there is more. For reasons I don't understand, people decided to tabulate this in another way too. Who knows why? So they say another tabulation. This is called QSS star. Have no idea how they came up with that name. I suspect SS means steady state, and the star, I suspect it means dimensionless. But this is a notation in the book. And this is the story. You know, for a wall, what is S for a wall? Who can tell me what S for a wall is? A over L, right? We have S is A over L, right? And so they say, all right, for an arbitrary shape, you have S equals A of reference over. So this is the surface area. This is some characteristic length that is established. And this is a correction factor. Of course, for a wall, that would be 1. But if it is, instead of a wall, something crazy, you have it tabulated, right? And this way you would have then Q is reference surface area times K times delta T over